Okay, so this is IMO Shortlist 204N6. Tells us that we define a Pn, which is a product of all positive integers x less than n, such that n divides x squared minus 1. So we want to find the remainder of Pn when divided by n. The first thing we should try is that we should try small cases of n whenever you see this. So let's say n equals 2. After a bit of trial and error, actually not trial and error, it's just one trial, you'll get that x equals 1 works, and multiplying 1 together is 1. So the answer is 1. N equals 3. After a little bit of calculation, you'll see that both 1 and 2 work, so the answer is 2. N equals 4. And then after a bit of calculation, you'll see that 1 works, 2 doesn't, 3 works, so the answer is 3. N equals 5. A few moments later, you should get 4. N equals 6. First, for now, you're seeing the trend that, hey, it looks like n minus 1. But then, when n equals 6, 1 works. 2 squared minus 1 is 3, doesn't work. 3 squared minus 1 is 8, doesn't work. 4 squared minus 1 is 15, doesn't work. 5 squared minus 1 is 24, which does work, so it's still 5. Okay, now you're starting to prove the n minus 1. So after a bit of trials, you'll see that proving this is actually impossible. An easy way to see why that is, take n equals 12. Then actually n equals 7 to 11, they all give this answer. But then for n equals 12, x equals 1 is okay. 2 is, this will become 3, which is not okay. 3, this will become 8, which is not okay. 4, this will become 15, which is not okay. 5, this will become 24, which is okay. 6, this will become 35, which is not okay. 7, this will become 48, which is okay. And ... until you realize that 11 is also okay. Multiplying these together actually gives 1. That's weird. So we've singled out this thing. Then after some more trial and error, you get some other values that don't work. For example, you'll see you'll see that if n is if n is 8, 1 doesn't work, 2 doesn't work, 1 does work, 3 works since it's 8, 4 doesn't, 5 works, 6 doesn't, 7 works, 8, there's no 8. So that actually also multiplies to 1. I neglected that earlier, sorry. So now we find these two, and it's easy to see that n equals 16, it's also 1. And another value, n equals 15, it's also 1. So it doesn't look like anything to do with parity either. However, we can now see that if n is a multiple of p for some prime, then obviously this. So now after a bit more of trial and error, you get 18 works. 18 works. 18. For here we're saying that a number works if the answer is n minus 1. So after a bit of trial and error, you get a few other values, such as n equals 20, 1 doesn't work. You also have n equals 20 doesn't work. But then you will notice that all of these are actually 1. So is there a trend? Say like this group of numbers goes to n minus 1, this group goes to 1. Indeed, the answer is in this form. So how do we get the precise answer? Well, firstly, we need to think about, since guessing the answer looks really hard, let's instead think about properties of Pn. First thing to notice is that x squared. If n is some numbers, then x squared and n minus x squared will be congruent mod x. I mean mod n. What am I writing? But this doesn't hold for some numbers. It holds for all numbers. So if 1 works, n minus 1 immediately works. So now we're just looking at the number of pairs of this thing. So we've basically proved this. No, we haven't. Never mind. Basically, now we know that the answers come in pairs. So what happens next is we try to classify these answers. Firstly, there is a type where it's pretty easy. When n is prime, you could just factor this thing out as x minus 1 times x plus 1. Then it automatically gives you that the only 2 solutions are these 2, which gives the answer as n minus 1. So primes are in this group. Let me just make those circles larger. Let's next try prime powers. Like, it's pretty natural, isn't it? Well, using the same factorization, you can see that we're just looking at P1. Actually, 1, let's say it's P to the K. So n equals P to the K. So we're looking at 1, P minus 1, P plus 1, 2P minus 1, etc. etc. So what this gives you is that the pairing is still there. Like, for example, the last number is p squared minus 1. This is p squared minus p plus 1. So the pairing is still there. Then after a bit of analyzing this thing, you will supposedly find that this for all p will multiply up to, this is k, sorry. This will multiply up to n minus 1. Okay. However, here, in the case that p is an odd prime and p is 2, these two are literally equal. Next, let's think about it. Let's say p minus 1 is x. Then let's multiply x times p to the k minus x. X, not n, sorry. Minus x mod n. So basically mod p to the k. This is equivalent to the p to the k is just gone, so negative x squared mod p to the k. But then by this, we have x squared is 1 mod p to the k, which means this is negative 1 mod p to the k. Hey, we can use this. Now if n is more general, say it's a multiplication of I equals 1 to n of p to the alpha, maybe we can split them into these cases, pi to the alpha I should use. Maybe we can split them into these. So Let's erase all of this. That's just experimenting. So I'd say I can erase this. So I'll put this a bit up here. Next, let's concentrate on this general case, more general case. So now we want to let me change that. Now we want to use the individual primes, pi. So let's say that we're taking mod p1 to the alpha 1. Then, well, how do we do this? Well, the answer is if we want this divides x squared minus 1. Since pi, we assume there are odd primes. We have these two don't both have pi as a factor. So x is plus minus 1 mod pi. P1 actually, but I'll just generalize it. It's actually pi to the alpha I. So now we have this thing to determine our x, because by CRT there are so we can use CRT to find this. Then observe that the pairing we observed from before is actually caused by switching all of these signs. So we have so how many pairs do we have? Well, if we have 2 plus of these things, we have an even number of pairs. While if there's only one of pi to the alpha I, we have odd. So what we have just done is, if n is odd, then we split into cases. I hate my Apple Pencil. We split into cases. First, if n is a prime power, we have, the answer is n minus 1. If n is not, the answer is 1. So that is part of our answer. Then we can just put these in the correct boxes. This is now extended to p to the k. This is now all odd non-pks. So we just, okay, now the final case is where n is even. So let's say it's 2 to the k times another one of this thing. Well, to be honest, this is pretty similar. We also have these. But the thing is, now we have a 2 to the k, a very annoying term out here. The way to solve this problem is by noticing that, firstly, x has to be odd now, and secondly, one of these cannot be a multiple of 4, so one of these two. Therefore, we basically need one of them to be a multiple of 2 to the k minus 1. Let's actually write this down. So x will be congruent to plus minus 1 mod 2 to the k minus 1. Then everything is similar. However, there is something to notice right here. If k actually equals 1, then the 2 out here, it's just saying that x must be odd. Yeah. Wait, have I done something wrong? Oh yeah, I haven't, never mind. I was thinking why when k equals 2 it's basically also this requirement. But actually that's because both of these are even, so basically k equals 2 is the same as k equals 1, supposedly. But then the number of pairs might change, so the answer might change. So now k equals 1, the requirement is just this. So next we combine these. Well, another of our standard pairings. Now k equals 1, I want to single this case out because basically we're just saying that, hey, x is odd in addition to this. So then we can like kind of not change this and then change the signs of these to get the reverse. And how many pairs are there? Well, for k equals 1, for k equals 1, after a bit of calculating, you'll see that the number of numbers that satisfy this is just this gives 1, this gives 2 each. So the number is dependent again on the number of these terms. So again, a single prime power, for example, 2 times p to the k. And this obviously also applies to k equals 4, at k equals 2, because basically the requirement is the same thing. So 4p to the k. Wait, hold on. Never mind. Don't mind what I just said. So 2 times p to the k, well, this gives n minus 1. Then for these, it actually adds in another factor of 2. Now, in this case, 4 times p to the k will also go to n minus 1. But as we just saw, 12 actually goes to 1. So let's analyze this case. Later. For now, we know that if k is larger than or equal to 3, we have the answer is 1. Okay, by now we are almost done. Let me just put these all aside. The only case that remains is 4 times p to the k, which is tricky. I guess you could say that. So all of this is now done. Let me just quickly conclude what we have got. Well, we have got that for odd numbers, prime powers make the answer n minus 1, while non-prime powers make the answer 1. So I'll just write it like this. Next, if it's even, we have 3 cases. 2 times p to the k, and others. Right now, there is a third case, 4 times p to the k, and we don't know. But this, we know it's n minus 1. This, we know it's, 1. So, what happens with this? Okay. Now we notice that this actually has a problem. There's the case 2 to the k not covered. And by pretty simple reasoning, you can see that except for 4, 2 to the k are all result in the answer 1. Because in this case, the answer is basically 1, 2 to the k minus 1, and then minus 1, 2 to the k minus 1 plus 1, and 2 to the k minus 1. So, pretty simple. Now, back to our case of 4 to the pk. Technically, this answer should equal n minus 1, according to this. But then the answer is actually 1, which means this is flawed. But why is this flawed? Let's check. So let's just say that right now, okay, P is 3. Then what happens is we have 1, 5, 7, 11. According to our pairing here, we have that x must be odd and that x is plus minus 1 mod 3, which actually does construct this thing over here. But the thing we missed is that right now we're pairing 1 with 11, 5 with 7. There are 2 pairs. What results in these 2 pairs? Well, the total mod is only 6. So actually, for k larger than or equal to 2, since 2 to the k minus 1 times pi to the alpha I, obviously the product of these, this is actually n over 2, which contributes to the times 2 factor. So this is also 1. Now, simple solution, just erase this. And we're done. And here goes our answer.